Hi everyone. In this video, we're going to look at pivoting tables of data using the tidyr package. So just like usual, we'll use our markdown to complete this and follow along with this activity here. So we've seen previously how we can use tidyverse functions to combine data sets because sometimes data comes to us in a form of being in multiple tables, which is not exactly ready for analysis. Sometimes there's this other issue of data coming in a tabular form that's not in the right orientation that we need for data analysis. So we may need to convert between what are referred to as wide and long formats of the data, different orientations of the same exact data set, in order to create visualizations potentially, or fit models. Sometimes your data needs to be oriented in a certain way to use functions in R. So typically, what's most common is that we need the data in what's called a long format, which has a relatively larger number of rows and a smaller relative number of columns as a way to represent the data, whereas a wide format is where we have a relatively larger number of columns or variables, and then a relatively smaller number of rows. So to emphasize the point that both ways to store a tabular data set, wide or long format, contain the same exact information. But one orientation versus the other, again, can facilitate model fitting, using functions for data visualization or other analysis methods in R. Hadley and the tidyverse team refers to this process of switching between the two orientations as pivoting data sets. But I want to point out that there's a lot of different terms for this type of reorganizing of the data in statistics. Sometimes there's a consensus way to refer to things, but I would say this one, in my experience, has a lot of different names. Sometimes this is referred to as melting the data or spreading or gathering the data. But for the tidyverse team, they refer to this switching between the orientations as pivoting the data. Okay, so we'll start by loading these packages here. Okay. So really, the tidyverse package contains all the functions needed for pivoting. We are just going to use the skim function from the skimr package for checking out potential missing values. And then the GG themes package will be here in case you want to use a theme from that R package, although it's not entirely necessary. Okay. So in this activity, we're going to be looking at an example data set on climate change. So journalists at the Washington Post organized and collected data from the National Oceanic Atmospheric Administration, NOAA, that has different measures of climate change across time. So they specifically obtained monthly temperature values for each of the lower 48 states, as well as every county in the United States between 1895 and 2019. And this data is publicly available on GitHub. So it's nice the journalists organized it and made it available there. So here's one visualization that the journalists made in a Washington Post article. It's pretty cool to see ggplot in the wild, so to speak. So this is a map that they made with ggplot, showcasing the temperature increases across time in the contiguous 48 states of the United States. Okay, we won't be making this type of map in this activity, but it is something that you could do with ggplot. Okay, So to start, let's import all these data sets directly from GitHub by using this code here exactly. Okay. So you should be able to run this, importing directly from the URL to the GitHub page. And we should be able to see these 4 data sets. Okay. So there's a lot of variables in these data sets. I put the descriptions of them here, which I got from the GitHub page. So it has the year of the measurement, the FIPS code, FIPS. This stands for Federal Information Processing Series codes, FIPS codes. So a lot of federal agencies use a unique identifier for each state and each county that's just a numeric ID. So every state has a 2-digit FIPS code or 2-digit ID that the federal government uses across its branches, as well as a 5-digit code for uniquely identifying counties in the United States. Okay, then we have the temperature in Fahrenheit, temperature in Celsius, FIPS code for the county, the state name for the name of the state that the county belongs to, the county name itself. Okay. And then this data set has annual average temperature change from 1895 to 2019. It also gives it the average annual temperature change across the months of September, October, and November. Okay, so this is averaged into the variable fall. And then we have it for spring, summer, and winter. So let's start by using Glimpse to explore some of these data sets more. Okay, so just gonna. So doing some exploratory data analysis. Yeah. Okay. So if we knit this, here we'll be able to see the variables that are in each data set, okay, which we already discussed, the FIPS code, year, the temperature observed for that year, the average across the entire year. And then, so this is telling us which state this is for. So for example, the FIPS code of 01, which we can see from the other data set here, FIPS code of 01 corresponds to the state of Alabama. And the FIPS code of 04 corresponds to the state of Arizona. 05 for Arkansas, and so on. So this first data set only has the FIPS code. It doesn't have the actual name of the state. So we'll see in a bit how, if we want to use this first data set with the full name of the state, we're going to have to combine the tables temp state and temp change state in order to take advantage of the fact that this one has the FIPS codes along with the full state name. Okay. All right. Okay. So Glimpse gives us a good idea of the variables in the data sets, the types of variables, looking at some of the first values, but it doesn't tell us anything about missing data. So to do missing data, we'll use the skim function. Okay. And this produces a lot of output, so we'll run it the first time here, but after I run it once and we look at it, we'll set eval equals false for that chunk so that it doesn't produce the output, but still shows the code. So we could see here from skim, looking at that output, that let's look one table at a time, I guess. Okay, so for the first table, we see there are 0 missing values for each of the variables, and they're 100% complete. So no missing values in the first table. Looking at the next table, similar case, 0 missing values for any of the variables, 100% complete for each of them. Okay, same with the third data set and the fourth data set. So actually, fortunately, there's no explicit missing values here. Okay. Now I want to emphasize that point that skim only detects explicit missing values. So again, NAs that are actually encoded in the data set. You could have implicit missing values where, for example, maybe a state is entirely missing from this data set. Let's say a row for Ohio is just not included. So there's no NA values for a row for Ohio, but it could just be completely missing. That would be an example of a implicit missing value. But those are actually, even though skim doesn't detect those or tell us about those, you could check, and there's data for all 48 of the contiguous United States here. So there's actually no implicit missing values either. But that's always something to be aware of, that those can show up in the data, but are harder to detect with methods like skim. That cannot tell us alone. We would have to do some extra digging. Okay. So any notable patterns of missing data? Nope. There is no missing data at all. Okay. Now let's work on reproducing this line chart showing the change in temperature across time in Michigan and Minnesota. Okay. So first off, looking at these data tables, which of the 4 tables is going to be most important for creating this plot? So we want the average annual temperature across the years for Michigan and Minnesota. So that's state level data. And then this has the temperatures in the state. So the first data set, temp state, is the one that we want. Okay. So let's create a new section. Line chart. Okay, so we're going to pipe this data set here into ggplot, create this line chart. Okay. And then we want to think about what are our X and Y aesthetics for this line chart. So X will be the year, Y will be the temperature. So X is year, Y is the temperature in Fahrenheit. Here. Okay. And if we want to make this into a line chart, which geom or geometry would we use? For a line chart, we use geom line. Now, if we look at what this plot looks like, it's very busy. There's a lot of lines. The reason being, this is for all the states. It has all the lines connecting every single temperature measurement for each state across time. So how could we trim this down a bit so that it's just for Michigan and Minnesota? Well, this is a little bit tough because we only have the FIPS code. And unless you know the FIPS code for Michigan and Minnesota, it's be a little bit difficult to do. We could use filter and filter by FIPS code and Google the FIPS code for each of the states, but we want it to show up as labeled as Michigan and Minnesota as well. So let's showcase our joining skills and join or supplement this data set with information about the state names themselves. So if we look at the temp change state data set, this data set has a FIPS column as well for the state, and then also the full state name. So these are really the only two columns we're interested in right now for this data set. So we can use select to make this a little bit easier to be working with, just keeping FIPS and state name. Now if we look at this data set, it just has the FIPS and the state name. And then the data set we're working with has FIPS and then the other variables. So we want to join these two data sets by the key variable FIPS. That's what connects or relates the two tables. So this is a good case of where we're most interested in the temp state data set. So if we want to join this data set with temp state, we'll use a right join. We can see how this looks now. So we have just temp state, looks like this. If we do a right join, all the right join did was essentially supplement or add on to this data set the state name. That's exactly what we wanted here. So now we can take this new data set that has the full state name here and pipe it right into ggplot. Okay. So that's not going to change anything about our plot just yet, but now we have the state name available in the data set. So if we look at this, what's getting piped into ggplot, here we can see we have the state name variable. And so if we want to subset to only Michigan and Minnesota, now we can do this using the state name column and the filter function. So before we pipe into ggplot, we'll add a filter. And we want to say where state name in Michigan, comma, Minnesota. And be careful with your spelling here because it needs to match exactly in terms of capitalization and spelling, or else it'll cause issues in your plot, but not necessarily errors. So it's a little bit tricky to catch. So make sure the spelling's good here. And if we run that, we can see the plot's already trimmed down quite a bit. So this is much better. We can see this is still just a single line, whereas we're wanting to produce a line for each of the two states, Michigan and Minnesota. So how can we break up the line into two groups in ggplot? Well, since we want to color the line differently based on each group, we can use the color aesthetic. So we'll do that inside AES. We'll add color equals state name. Okay. That will use the default ggplot colors, this teal color and this salmon color, which are not colorblind friendly as a reminder. So then we'll make sure that that's colorblind friendly by adding a scale color colorblind friendly layer. Okay. We can add a black and white theme to match what's in the activity here. Okay, so it's getting a little closer. Next, we'll add all the labels to update the plot. Okay, so before the theme, maybe we'll add a labels layer. Make sure to get your plus sign in there. So we'll add a title, x-axis label, y-axis label, the caption. So for the title, temperature of Michigan and Minnesota. We'll do that. For the x-axis label, we'll say year. For the y-axis label, say temperature in Fahrenheit. The caption, data source, okay. All right, so that's already looking a lot better. Almost there. Now here, just a couple small things. So we want to move the legend to the bottom, and we want to suppress the legend title. So to move the legend to the bottom, we can add a theme layer. And then we want to suppress the legend title. So one way we can do that, there's multiple ways, but one way we can do that is, since the legend was a result of specifying a color aesthetic, in labs, we can specify color to refer to the legend title. Then we can make it empty by doing an empty string. So there we go. And there is our plot. Okay. So that was the line chart. And a typo in here, the data actually goes till 2019 if you look. Oh, oops. Temp state. If you look at the max, it actually goes until 2019. All right, so let's knit this and just take a look, see how this is looking. All right. Okay, great. So there's our line chart. Actually even update that in the activity. All right, perfect. Okay, so none of that was actually pivoting the data yet. That was just exploratory data analysis, revisiting, combining data sets, and creating a line chart. So now we'll look at using the pivot longer function to reorient our data set from a wide to a long format. So specifically, we're going to be looking at modifying the temp change state, or we're going to be creating a data set called temp change state long, a long version of the temp change state data set. Okay. We're going to be creating this data set, which will be temp change state, which is currently in wide format, and we're going to make that into a long format. So if we look at the currently wide data set, what makes this a wide data set is that we have multiple columns that could be condensed into just 2 columns. So we have the temperature change on average in the fall for each state, the temperature change in the spring, summer, winter, and then the annual temperature change on average in each state. These 5 columns, fall, spring, summer, winter, and annual, could all be condensed into 2 columns. One that indicates the value of the temperature change, and another column that indicates which period or season the temperature changes for. That would be fewer columns, but create more rows in the data set. So that's why we refer to this reorientation as pivoting the data to a longer format. And that's why we refer to this currently as being in a wide format, because there's more columns being used to represent the data than we potentially need. And I want to emphasize, it's not that one is uniformly better than the other, a long versus wide format. Just sometimes it helps with analyses. So, for example, if we want to create a line chart of the temperature changes, or a plot of the temperature changes, and we want to color by the season, we need the season as being a variable in the data set, not as information that's stored in the column names. That makes it harder to access for functions like ggplot. So we want to, typically, data in a longer format is easier to work with in the tidyverse. In most programs, it's typically easier to work with data that's in a longer format. However, you commonly get data in a wide format like this simply because it's easier to enter data that you have stored. When people are entering data manually, it's easier to do this in a wide format. All right, so we're going to take this data set temp change state and make it longer. So we'll use pivot underscore longer. Okay. So the arguments we have are data, which is always the first argument to most all tidyverse functions, because this allows us to pipe data sets into the function in a nice readable way. The next argument is the columns that we want to condense down or that are to be reshaped. The names to argument is describing the name of the variable that will keep track of what the column names were or what the groups were. In this case, these are the groups. So this will be the new variable that has these values. We just get to pick its name. And then there needs to be another column that has the values themselves that were contained in the columns before. So the temperature changes themselves. So we'll call that variable change, and we get to pick that. So that's what the values to argument specifies. So first, specifying calls. So the columns that we want to condense down, we are going to say fall through winter. So we can use this called this tidy select syntax, it's called, to select ranges of columns. And then we also want to select the annual column, which we had to specify separately just because it wasn't, there was this max warming season variable in between, so it messed up being able to select it in the same way. Okay, but we're just selecting all these columns together at once as the ones we're going to condense down. We're going to names to, so the new variable that we're going to make that will keep track of the variable names from before, we're going to call period. So we do that in quotes like this. And then values to, going to be the name of the data or the column in the data that has these numbers from before. So we're going to call that change because it's the temperature change. So now if we run this, you can look at the long version of this data set. So this has the same exact information. You can see minus 0.196 was the temperature change for the fall. For Alabama. We can see for Alabama in the fall, here was the temperature change, and so on. So now this data has been reoriented or pivoted into this longer format. Okay. All right. So we'll also do that for the county data, which, because the variable names are actually the same across the data sets, we can pretty much just copy this code and then change, instead of state, we'll say county in these two spots. So make sure you update it in both spots. And then that will create a long version of the county data set as well. So that one before looked like this. That was the wide format for the county data. And then we had it for the county data, the long format here as well now. Okay. So with these new long versions of the data set, let's first look at the 10 largest temperature increases across all seasons and counties. Okay. So how can we do that? So displaying the So we're going to use this county data set, and then we can use the slice max function to say we want the 10 largest values for the change variable. So the 10 counties that changed the most in terms of temperature, or had the largest increases in temperature. Okay. We look at that. You can see printing the 10 largest temperature changes. There's some notable patterns in the data set. Every single period is for winter. And when you look at which states the counties were in, these are all very northern states, also very inland. So traditionally, when you think about climate change, at least for me, I think of like Florida or coastal states. But actually, when we're looking at the data here, this is showing us that the largest increases in temperature where there's warming the most is actually in these more inland states. So these are northern Minnesota counties traditionally, and then North Dakota. So both very cold places, and then in the winter. So it's the coldest places that are warming up the most, it looks like. So that was a bit of a surprising result, I think. All right. So now let's look at, that was just 10 particular counties that had the largest increases. We can use side-by-side box plots to visualize the distribution of temperature changes within each season. Okay. So let's look at reproducing this box plot, and we're going to be looking at the state level here. Okay. So creating side-by-side box plots. So we're going to use this long version of the state data set, state temperature changes, and then we're going to pipe that into ggplot. Okay, so looking at this data set, it's good to think about for the box plots here. What is our x-axis variable and what's our y-axis variable? So x is the period, y is the change, the temperature change. And then to make side-by-side box plots, we can add a geom box plot layer. So here we can already see it's gotten us quite a ways in. It's almost already resembling the plot we're trying to get. But we have some stuff we need to fix up. So for one, we only wanted fall, spring, summer, and winter, but there's an annual box here. So we want to get rid of this. So there's always a few ways we could do this. One of which is that we can use filter to subset the data to only these seasons, fall, spring, summer, and winter. We can use filter before the ggplot to say where we want period. And then we could say in fall, spring, summer, winter, or even shorter, since we just want to exclude one group, annual, we can say where period not equal to annual. Okay. If we run that, we can see the annual group is now excluded. Let's see. Another major thing about this data here, this plot, is that period is a categorical variable. And if we think about it, which type of categorical variable is it? It's an ordinal categorical variable. So there's a particular ordering to the categories. Fall comes before winter, which comes before spring, which comes before summer. But right now the groups are all jumbled. The order is not how this happens. It doesn't follow the ordering of the categories. So we want to reorder these groups in a sensible way. Anytime you're creating a plot, like a bar chart, a bar plot, side-by-side box plot, if you have an ordinal categorical variable, you want to order the bars or boxes the same as the ordering of that variable. So to do that, there's a few different ways we could do that. One is to use factor relevel. Okay. FCT relevel, and then we'll say, let's see, fall, winter, spring, summer. Okay. So let's say fall, winter. And make sure we're careful with the spelling and capitalization again, because this needs to match exactly. If we do that, now we can see we have the categories in the order that we want. Next, we will color the insides of the boxes blue to match this. Okay. Since we're not coloring differently depending on which season it is, we're making this constant across all groups. We specified this color aesthetic now just inside the geom, not inside AES. And specifically to change the coloring of the boxes, we use the inside of the boxes, we use the fill aesthetic. The color aesthetic, you can try it out. It changes the outline coloring of the boxes, which we could do, but we'll just leave it as the default black coloring here. And we'll also add a black and white theme again. Okay. And now we'll update some of the labels for the plot. So we'll take, we'll start with our labels from last time and update that to save ourselves a tiny bit of work. just because the caption's the same. Y is still temperature. Now it's temperature change, Fahrenheit. X is the season, although fall, winter, spring, and summer, I think is pretty clear what those are describing to us. So we don't necessarily need a x-axis label here. We can make it empty. And then for the overall title, state level temperature changes. And that gives us this main part, this title up here. To get this part, which is a little bit smaller of a font size and it's not bold, we'll actually use the subtitle argument of the labs function. So to produce that subtitle, and there we go. That is our side-by-side box plots. Okay, so let's knit this and look at the overall document. So what we see, oh, actually, it should be 2019. Let's see. 2019. Okay, there we go. So what we can see is that these, although it's only 10 observations in the whole data set here, it is the case that winter appears to be warming the most typically. So looking at this plot, interestingly, all the seasons are warming. So it's warming overall through all parts of the year here across the United States, but winter is warming the most. Okay. All right. Update that because of the, update this in the activity as well. Okay. Pivoting a data table to be wider. Okay, so moving on from the box plot now, let's look at how we can pivot data from a long to a wide format. This is a much less common thing that you would need to do, but it is still possible that you run into this when trying to analyze real data. So we're actually even going to have to use a different data set because it's hard to find ones where it's helpful to pivot to a wider format versus the longer version that the data set's currently in. So let's load this data set, US rent income, from the tidyr package. Okay. Okay, so if we look at this data, and we'll use Glimpse to take a look at it. Okay. We can see that in this data set, and we'll open it up in the viewer here, we have Here's the FIPS code. They call it the GeoID in this data set. The income estimate from, let's see, we want to look at the help file for this to get details about the data set. Okay, data from the 2017 American Community Survey. This is kind of like a mini US Census that happens more frequently. The census only happens every 10 years. The American Community Survey, commonly just called ACS, happens more frequently, but asks a lot of variables. Asks a lot of questions about general United States citizens. So this one has income, median income for each state, and the median rent estimate for each state for those who rent. And then a margin of error, which describes uncertainty in the estimate or expected variability in the estimate. All right, so we see, we have the estimates for income and for rent, but this is in a longer format currently. Ideally, or not ideally, but an alternative way to store this data would to have a income estimate column, an income margin of error column, a rent estimate column, and a rent margin of error column. So instead of these 3 columns, we could have 4 columns representing the same data, which would have less rows. Okay. So let's use the pivot wider function to create a wide version of this data set called US rent income wide. So we'll use US rent income. We'll pipe this into pivot wider. And then the pivot wider function takes the arguments, the data set is always the first argument that needs to be reshaped or reoriented. Then the ID columns are sets of columns that uniquely identify each observation. So in this case, the GeoID and the name columns are ID columns for this data set. So GeoID through name. The names from argument tells us where are the new variable names going to come from. So in this case, the variable column has whether it's for rent or for income. So we want to have new income and rent columns in this new wider data set. So we'll say names are going to be coming from the variable column. And then the values are actually coming from the estimate and the margin of error columns. So let's just start with just estimate, what that would look like. Okay. If we just get the values from estimate, okay, we have, here's the long version of the data set, and then here's what it looks like when it's wide. So this loses the margin of error because we didn't include it, but we go from this, where we have income and rent stuck in the rows, and then now we just have the estimates of income and rent, and they each have their own column for each state. This might be helpful if you wanted to do like a linear regression between income and rent. You would want it in this format rather than the longer format here. This would be difficult to fit a linear regression model or to make a scatter plot with the data oriented in this way. But we lost the margin of error here, so we can also include, if we include in the values from column, We include the margin of error as well. Pivot wider has this really nice property. It recognizes that we now have two estimate columns, one for income and one for rent, and then also the margin of error columns. So it does a really nice job of naming the columns automatically that it generated for us. So now this is in the wider format, which again makes it easier maybe to make a scatter plot or to fit a regression model. So we'll reproduce this bar plot, actually a bar plot, using the now wider data set that we've just created. Okay. So let's see. Okay, so using this. Okay, so to create a bar plot, we'll pipe into ggplot and then specify our X and Y aesthetics. So this is a horizontal bar plot that's been flipped already. If we think about it when it was vertical, that's how because we start with a vertical bar plot or bar chart. So think about the vertical bar plot. What is our X and what is our Y variable in that case? So when it's vertical, the X is the state and Y is the rent to income ratio. Okay, so we have state, which is given by the name variable, and then Y is the rent to income ratio. So we'll use the estimate columns. So you can do this like this, where you actually calculate that ratio in ggplot. And that works. It will let us do this. Then we use geom call to make the bar chart like this. Oop. Run this. Okay. And that gives us the vertical bar chart to start. And we have the ratio. It's the y-axis. Okay. So you can do it like this, and that works perfectly fine for the ratio. This does make it a little bit trickier to sort the bars based on the ratio, since we're just calculating it now just here. So sometimes what's better is to do this explicitly beforehand with a mutate, with a call to the mutate function. So let's do just that. Let's use mutate. And let's say we'll call this rent income ratio. And then instead of the y being this, we'll actually do that new variable that we're making. That gives the same plot here. But like I was mentioning, this makes it easier now that we have this variable explicitly in the data set. Due to the mutate function, we can now reorder the height or the bars based on this variable. So we can say around name, we can say factor reorder. And then we're reordering based on the income ratio. So this is essentially sorting the bars. Okay. All right. And that looks good now. We could call it a day at this plot and just leave it as is, right? No. Okay, so we'll keep fixing it up, right? This looks awful right now. So let's see, what can we do first? Let's flip it to, or before we flip it, let's add some labels. Okay, so we have state, rent to income ratio. So add some labels. So let's see. X is the state, which we can actually just maybe leave empty. Y is the rent to income ratio. And notice that there's no units on this ratio because the dollars for rent and the dollars for income cancel each other out. And these were actually the median rent to median income ratio, if we want to be precise. Okay. The title. And then we can add a caption saying where the data came from. Always good to do. You never know where your plot will end up. So it's good to add in the data source because you might not be there to answer someone's question about where's the data for that plot, or where did that come from? So it's always good to have a little note of that on your plot. All right. Great. And then now we'll flip the plot to a horizontal format. Great. Okay, so we're almost there. And then we can add a black and white theme. Perfect. If we want to color the insides of the bars to be blue, we use the fill aesthetic inside geom call. Okay. As a reminder, since we want this to be constant across all groups, across all bars, we do it inside geom call. If we wanted the color to vary based on some other variable in the data set, we would do it inside AES. We would specify the fill aesthetic inside AES, but we want it to be constant here. Okay, this doesn't look great by default. It's kind of hard to distinguish between the different bars when they're very close. So you can outline the bars with black. That helps that issue a little bit. So we do that with the color aesthetic. Makes the bars a little bit easier to distinguish from each other. Okay. All right. And then this is still a little bit crowded with all the states. You could keep this and maybe decrease the font size of the state names. What we're going to do is just subset to just the states with the 10 highest rent to income ratio and the states with the 10 lowest rent to income ratio. Okay, so there's a few ways you could do this for sure. One way would be to take the data set that we piped into ggplot, store it. So we'll call it maybe like ratios. And then what we'll do is we'll take ratios. We'll say we want the, okay, so if we store this, let's take a look at what that looks like before we keep moving, I guess. So ratios, it's the same data set as before, but now it has the ratio column. We can use slice max to get the 10 largest. Let's see what that variable is called. Rent income ratio. We can get the 10 largest. And then we can get the 10 smallest using slice min. All right. Now we have these two data sets, the max and the min. We sort of want them stacked on top of each other. We want the rows to be stacked on top of each other. So there's this nice dplyr function that is called bind_rows, which allows you to concatenate or append two data sets by the rows to each other. Now, if we look at this data set that results from using bind rows, we can see we have 20 rows, 10 being those with the smallest rent income ratios and 10 with the largest. So that's one way to do that. Right. There'd be other ways as well, but okay. And so this is the data set that we want, and we're going to pipe that directly into ggplot. So now if we run this, this only has the 10 largest and 10 smallest ratios for the states. So we can see there's certainly some regional trends here, right? North Dakota, South Dakota, Iowa, Nebraska, all very Midwestern states have a smaller rent to income ratio, indicating that maybe it's a little bit more feasible to live there. Cost of living is relative to the income of people there is a bit lower. So good for them. And then unfortunately, people living in Hawaii, California, Florida, seems like it's expensive to live there relative to the income that people make there. So yeah. So that is, let's see, I think that's it for that plot. Yeah, great. Okay, so we'll knit it one last time. And that is it for pivoting to wider and longer formats. Okay. So again, most common is that you'd be pivoting to a longer format from a wider format, although both options are available using tidyr in the tidyverse. So that's it for this activity. Thanks.